says let X be a random variable that represents hemoglobin count, HC. And what they did here is they collected data, 14 healthy, so N equals 14, healthy adult women. And suppose that a female patient is 10 laboratory tests. Oh, they're giving me two numbers here to throw me. So there's the sample size is 10. And the 14 isn't how many healthy women it is. The 14 is what a healthy woman's HC count would be. Okay. We're going to find the mean and standard deviation. So if I just hit use salt, we should be able to get that data, which we have. Here it is here. And then if you hit descriptive statistics, the mean is 15.4. And the standard deviation of the sample is 2.9515. So it's pretty much just hit the calculator, salt, and then go to the descriptive statistics. They want the answers to 2 decimal places. Well, this one only has one. And the other one, if I round it off, becomes 2.951, so it's 2.95. Now, in this story, this woman had 10 different blood tests. So I guess I've been really careful. I know that they do that. I remember when I was in intensive care, they took my blood levels like every 4 hours. I mean, I couldn't get to sleep for the buggers. So they do that so that they can discover what the true value is. And also, I think they do it to see if there's any change through time. So in this story, there should be a significance level. And there it is. And that's one of the dumbest questions in the world, because use that, and then they ask you, what number did you use? Now, it's kind of hard to get that question wrong, right? Now, we also want to use this sentence. Does this information indicate that the population average HC of this patient is higher than 14? Now, if you're higher than 14, you're this one. The second one, the guy they're calling H1, the one I prefer to call HA, if you do that guy, he is always going to go second. And in this case, higher than 14 tells me it's this one. And isn't the first one always equal to 14? So see these two here, although they're probably going to be examples of this in every question, these two in the bottom, just totally ignore them. They're never going to be true. So there is the null, that her average is 14, just like a healthy person. And the alternate is there evidence to show that she's actually higher than 14? And the standard question here is, do you know sigma, do you not? So I don't, so it's a student. Is sigma known or unknown? It's unknown, so that makes it this one. And I think in most of the questions I have the same 4 choices and it's the same answer. It might not be in position 3, but that's it. Now we've got a test statistics, which means a t value, and then we got a p value to get. So I go back up here and I use salt. Only what salt is going to do this time is it's going to get the t and the p values for us. So let's see if we can set this up. The sample mean, we already found it. It was 15.4. Let's try that again. 15.4. The standard deviation is 2.95 to 2 decimal places. And the sample size was 10, which is perfect. In this hypothesis, weren't we looking for, if I bring it up again, bigger than 14. So bigger than 14. So you put 14 in here and you're looking for the one that's bigger than. So that's everything that I need. Oh, and make sure it's one sample T as well. Ready to go, generate result. And the T statistic that they're talking about is about 1.5 with a lot of zeros. And the p-value is 0.0838 and lots of other stuff. So 0.08, remember that, 0.08. So the T statistic was 1.5. And instead of giving me a box, which they should have, where you just type in 0.0838, whatever they want, we go here and we have to find out which interval has 0.083 in it. And I believe it's that one. Would you agree? 0.0838. It's in that range. And we are looking for a less than, so we look for a little picture that's got a less than in it. Where is my p-value? Oh, it's more than, sorry. We're looking for a more than 14, so I look for a guy that's big on the right, which makes it that picture. If I was looking for something on the left, it would be, you know, just a little guy over here. Okay, the alpha value that we're comparing this against is 0.01, and the p-value is 0.08, roughly. Okay, so I'm going to leave this for a second, just so we can see it, because we're not all auditory learners. A lot of us need to visually see it. Those two guys are the two most important guys in this process, because these are the two guys that are going to tell me whether I've proved what I was hoping to prove. And the test for that is your p-value less than alpha? And so is 0.08 less than an alpha of 0.01? Is that a yes or is that a no? Is this less than that? Good, you're shaking your heads, that will do. No. And when it is no, it is not significant. So that's the important thing. It's not significant. We haven't found anything very useful then. So I'm now going to return to the homework and show how we kind of state the same piece of information, right? Based on all the stuff, is the data statistically significant? The answer is no, it's not. So it's not statistically, could mean it's number 2, or it could mean it's number 4. When it is not statistically significant, you always fail to reject the null. So when it's not statistically significant, you always do the fail to reject H null. And when it's not statistically significant, you always pick the one that says there's insufficient evidence. So what that has told us is that this woman, and we haven't been able to show that her level was really anything exceptionally high, right? It was just a normal kind of variation that you would get. I'm going to go back to this question and change the rules a little bit. Suppose we had given you a 0.1 significance level and that the p-values ended up being, as it should, the same number. In this world, isn't the p-value less than alpha, 0.08, is less than 0.1? Isn't that a yes? which might seem like, well, how can you say that it's not statistically significant? And then you say, look, if I change the alpha, it now is statistically significant. It's not significant at the 0.01 level. It is significant at the 0.1 level. So all that is telling us is that when we say something is statistically significant or not statistically significant, doesn't it depend on what alpha we use to do the test? On the other hand, suppose the p-value was 0.123. It doesn't matter which of the three standard significance levels I pick. I could pick 0.1, 0.05, or even 0.01. Won't the answer be no every single time? So it's not that you're guaranteed a significant result or you're guaranteed a not significant result. What I'm trying to get across here is the significance level does make a difference. If p-value is tiny, you're going to get yes all the time. If p-value is really big, you're going to get no all the time. But isn't there a kind of middle ground where the p-values, sometimes it's going to be significant and sometimes it's not. And in those cases, it depends on what you chose for your alpha. So you are not allowed in the scientific world, or you shouldn't be allowed, to pick your alpha after you've done the question. In other words, you wait until you find out what p-value is, and then you say, I was always going to use an alpha of 0.1. Because that's basically cheating, isn't it? It's a bit like looking at the end of the movie to see how it turns out, and then saying, well, I knew at the start it was going to be that. Right, you're basically cheating. So we don't like that. It's bad. Okay, are we okay with that question? I know I drifted a little bit, but we're comfortable with the process. Right, so let's do another one. Snow avalanche, I'll miss that one. Let's do 16 then. And 16's got an interesting theme. It's about how long you're going to live if you stay in, evidently, Hawaii. A national newspaper reported that the state with the longest mean lifespan is Hawaii. So people live longer in Hawaii. And that mean span is 73. A random sample of 20 obituary notices in Honolulu came up with these ages that the person died. Okay. There's 2, 4, 6, 8, 10, 12, 14, 16, 18. There's 20 there. So we're going to use SALT to get the mean and standard deviation. So hit that guy. There's SALT. There's all the numbers, all 20 of them. Descriptive statistics, and the mean is 71.4, and the standard deviation is about 20.65 to 2 decimal places. So 71.4 and 20.65. Assume that it's approximately mound-shaped. Does this indicate that the population lifespan for Honolulu resident is less than 73 years? Okay, there they go. This is the thing we're wanting to prove. Does this indicate that it's less than 73? So people said it was 73, you collected some data and you're not so sure that they told the truth. Maybe it's changed, maybe it got different in the last year. The significance level is 0.05. We want to see, in this case here, it's less than 73. Okay, there's dot 1, 2, 3, 4, and 5. Which one of those is the right dot for this hypothesis test?
3.
That's it. You all see the pattern? Trying to prove it's less, and this is always equals. Right. Now, what guy we're going to use? We're going to use the student's T. Do you see it's the same sentence? They just put it in position 1. These two guys here are going to come by using SALT again. So let it finish doing its thing. Inferential statistics. There's the mean. There's the standard deviation. There's the sample size. The number that we're trying to do was, I believe, 73. And we're trying to see if it's less than that. So I'll generate the results. And the T statistic is negative 0.346. And the p-value is 0.366. Okay. Oh, I've got an idea. This might work. And it might not. I'll try it anyway. There's basically the question, or at least most of it. And if I put this guy beside it, can you see the null alternate? There's my T statistic, there's my p-value. In here, I put my, hope I'm in the right question now. In here, I put this the sample statistic, which is this guy. If ever you're testing less than, the T statistic is always going to be a negative number. That's the answer to 2 decimal places. And the p-value is what, about 0.36 roughly? 0.36. Oh, there it is. It's there. No, it's not. 0.36 is that one, right? It's even bigger, that one. We are looking for a less than story. So that's a less than story. Okay, is this p-value less than 0.05? Definitely not, right? And that means it's not statistically significant. Insufficient evidence. Dot 1, 2, 3, or 4. Which one of those do we use in the context of this question?
Four.
2.
Well, it's either 2 or 4, so let's see the choices. At 2, we reject a null hypothesis, it's not significant. And at 4, we fail to reject it. So it's 2 or 4. It's always going to be the same sentence. And it's the
graph again.
There's the graph. Why is it this bit? Well, that's an old number, isn't it? It's this one. It was a negative number to the left. Okay, so back to this fella. You always fail to reject the null hypothesis when it's not statistically significant. Those two always go together. You never have them separated and still make sense. I'm not sure putting that in one screen was a good idea, so I don't think I'll do it again. Plus, I'm not quite sure what size screen some of you are using. So there, I'll make it nice and big. So evidently, the obituary didn't prove anything. I mean, it was a little bit less than 73, but that could have just been randomness. Right. Now, if you did it and it was 90, that would prove that it was a lot bigger. If you did it and it was 62, that would probably be evidence that it was a lot less, at least based on the data that we've got there. Don't want the salmon one. I think this is the second last one or the last one. It's the second last one. Let's do this one then. They're using tree ring data to try and find out how old an adobe settlement in North America was. And various pieces of wood came up with different years. The science is not perfect, right? There's always some wiggle room. So we want to find out whether this particular set of data, what the mean and standard deviation is. So I'll use SALT. And descriptive statistic, and the mean is 1268. And the standard deviation is 37.29. So that was pretty quick. So that guy is 1268. And this guy here is 3729. So according to this data, the average age was about 1268. They believe that this particular place, based on other evidence like pottery and so on, was actually being inhabited around about 1290s. So there's, what, 30 years difference between what one said and what the other said. That might be just within the usual variation, right? Not significant, or it might be. So let's find out. Use SALT. Oh, we need to know what we're trying to prove. Does this information indicate that the mean of the tree ring is different, right? So the keyword here is different from 1292. And there's only one of them that has the not equal sign, right? That one. So it's the third dot. Now, what sampling distribution? Okay, dot 1, 2, 3, or 4. It's the same question every time. Where have they hidden the right one this time?
4.
Isn't that and that the two things that make it happen, right? Now, when it says, what's the volume of this test stick, can't even say it today, significance level is 1%, put that in. And let's do SALT then and get the T and P values. Oh, and I forgot to check 1292. So we want to see, is it different from 1292? Oh, perfect. Generate the result. And in this case, it's a negative 2.03 for the T, and it's a 0.07 for the P value. So the T statistic is negative 2.03 and a P value of 0.07 would be that one. It's a negative number. So we're looking at negative, guys, two-sided. Oh, that one. Is it statistically significant? Okay, is 0.07 less than 0.01? Question?
So when it was the negative 2.03, it said round the to the nearest 3 decimals, and I was curious, like, would it ding you there for only putting 2?
It probably would. I've just
So
been
there should
lazy.
be like a 5. It was negative 2.035.
Yeah.
Okay. I just was curious, like.
No, just me being lazy and not reading the question, because I think one of the other questions it was 2, so I just kept on doing 2.
Yeah.
I have a
Yeah,
question about the p-value.
Yes.
So I don't really understand that part right there.
Okay. I have a number that was 0.07, right? That's what we just got a few moments ago. So the exact value of the p-value is 0.07. One of these intervals contains 0.07, right? This interval, you'd use it if the p-value was bigger than 0.25. Well, it's not. If it's between 0.1 and 0.25, no. This one, if it's 0.05, oh, that's the right one. 0.07 is in this range.
Oh, okay. The 0 at the end was just really throwing me off.
Yeah. I guess you could call your p-value 0.070. And then it would probably fit better. Is 0.07 less than the significance level being used, which is this one? And the answer is no. And when it's no, then insufficient evidence, right? And let's do it for one last time. Which one of these 4 is the one that you pick when it's a no? 1, 2, 3, or 4. Which dot do you use when it's a no?
Fail to reject, number 4, and not statistically significant.
Yeah. So not statistically significant and fail to reject. They always go together, right? Now, can we pretend the answer was yes? Let's suppose we get different numbers and we got a yes. Which one of those 4 would we use for a yes? Think of the exact opposite of this one.
The first one.
And these are the only 2 choices. The top one's a yes and the bottom one's a no. These other 2 are kind of half right and half wrong thing. And we don't use half right and half wrong, right? When it is a no, you fail to reject the null and it's not statistically significant. When it's a yes, we do reject the null and it is statistically significant. I know there's 4 shots, so I guess you could just keep guessing until you got it, but it's better if you know the answer. And the last one's just talking about what would happen if you did this or that. And that is the end of that section. So we're now about to start our next section. I am going to share for a moment what we have got left to do, in case we didn't see it last time. That is not the one I wanted to click. I wanted to click this one, right? Maybe reduce its size a little. There we go. We just finished 8.2. We'll be starting today 8.3. And we're going to still be on hypothesis testing, but we're going to do it with the proportions now instead of means. When you did it with means, there were 2 flavors. 8.1 was when sigma was known and it was z-scores in normal distribution. The one we've just finished 8.2 was sigma unknown, t distribution, right? So there are 2 different nuances on how you do it. 8.3 is about proportions. There's only one version of proportion, and they're all normal. There isn't a t-score. And then we do testing for differences, and that one's actually a long section. And that's all hypothesis testing finished. And then we have 2 more sections, chapter 9.1, where we look at scatter diagrams in association. And then we do linear regression. And that is us finished. And I hope, yes, if you look over here, do you see that all these guys are due on Sunday the 6th of December? Do not wait to Sunday the 6th of December at 7 p.m. and think you're going to get this homework done in time.
So 8-2 isn't due this Sunday?
Nothing is due now until that last Sunday. So I'm just putting everything that's left into one big homework assignment, and it's all going to be due on the same day, because that is pretty much us finished.
Are you gonna change 8-1 then?
Say again?
Are you gonna change 8-1? Because that one says
No,
it.
8-1 you have got till the 22nd. That
Oh,
one you probably should have done this Sunday. So you've got
Okay.
more time than you need, I think. But everything else, 8-2 to the end, you've got until, what's it, 2 weeks and a bit, 2 weeks and 4 days or something. But you've got to remember Thanksgiving is in there. So there's going to be a big chunk of time that you're not going to be doing any homework, right? So I suggest very strongly that you get 8-2 done tonight, or definitely tomorrow night, and as much at 8-3 as you can by Friday, because hopefully we'll get it finished by Friday. That way you'll have a much easier time over Thanksgiving, because you won't have anything to worry about, it's done. And then when we come back after Thanksgiving, we'll get these guys here finished, and that should be us. At least that's the plan. Any questions about that? We good? Oops. Yeah.
That was the end of 8-2.
That was the end of 8-2. Yes, we finished 8-2. Right, here we go. Just getting myself set up. Why don't you say hi for attendance while I do all this? I'm almost ready. Just writing down some formulas. Right, I'm ready. Let's kick it over. Oh, darn it in space. You've went weird on me. You can't see what I can see right now, but my darn Zoom has gone strange. Right, let's kick in. And golly, darn it, I've got this window that keeps popping up at the wrong place. And I don't know what the heck that's doing there. Okay. So what we're going to look at here are questions where you ask someone, oh, have you ever been to France? And they say yes or no. Do you like sci-fi movies? And they say yes, no. It's a simple question where there can only be two choices, yes or no. And we tend to count the successes, and we come up with a value, which is very often called P. So, well, let's do an example of that. That's a good way of doing it. This is a hypothesis test based on a single proportion. I'm going to do this question by hand, just to show you what it's like. And the good news is that SALT does most of the calculations for you. So, N equals, there are 33 people, because that's what Zoom is telling me. And I am going to ask you a question. And I'm going to count thumbs ups. So if you stick your thumb up, I'm going to choose it. So we have to figure out a question that at least some of you are going to say yes to. How many of you have been to a restaurant, you know, like a sit-in restaurant, right? Where you go in and sit down and have a meal rather than a takeaway, right? How many have been in a sit-in restaurant in the last week?
Are we even allowed in sit-in restaurants anymore?
We are. I was in one yesterday. I believe you're allowed to sit outside in the freezing cold now. Okay, it looks like 6. There was about 6 a few moments ago. It's total mystery to me. Did you know that COVID is intelligent? COVID knows that after 8 o'clock, it's allowed to attack people. And it knows that if you're inside, it's allowed to attack you, but if you're outside, it's not. And if you riot, it's not going to give you anything. But if you go to church, it's going to attack you. Isn't it interesting how COVID is so intelligent like that? It's the only disease in the world that is so selective. We can even tell when it's going to attack you. And that's why all the government politicians have made up these nice rules to save our lives. I had to get that out of my system, right? But politicians are dumb, agreed? They just are. I think it comes with the territory. Okay, so I'm going to turn this fella into a decimal, and then I'm going to cheat by making up my question. So 6 divided by 33, it's about, I know it's not exactly that, but can we call it 18%? Okay. And I'm going to test, I think, the real proportion is less than 25%. Right. So I think this is evidence to prove that the real proportion, right? People in Bremerton will say that you're just a sample of Bremertonians or Kitsap County people, right? That it's less than 25. Now, I need the significance level because that's going to be in the question. Which one do you want me to pick? There's only 3 to choose from. So which one shall we do?
Can we not do 1 or 5? Can we do the third option?
There's 1, there's 5, and there's 01. So 2 of them have a 1 in it. So
oh,
which?
no wonder.
Okay.
01, I guess.
01, right. Now, that is the 1% significance level, right? Do you know that's the hardest one to get over, right? If I can say it's significant at that level. That really means I'm only going to be wrong about 1% of the time. So I'm pretty sure that whatever I say is going to work. Right. So we've got this guy, and we've got the 1%. And there's a few other things that you need to calculate. There's another guy called Q hat. That's been a while since we've seen Q hat. Do you remember what he's equal to?
One minus p hat.
Yep. In this case, that's 0.82. So it's a bit like 18% of you said yes, and the other 82% had said no. Are we good? Right, I think I've got all the pieces. So let's calculate the z-score. For this data, the z-score is p hat, take away p, divided by the square root of p hat. Oh, no. That is coming, but not yet. I forgot a very important starting point. Don't you always have to have your null and alternate hypothesis before we even think about anything? Right. So in this case, I think that the proportion is less than 0.25 and 0.25. Have you noticed I don't do mu, I do p? Isn't mu the letter we use for sample mean, and isn't p the letter we use for sample proportion? Right. Right, now I can do my z-score. It's p hat, take away p, over the square root of p, 1 minus p, over a. P hat 0.18, take away p 0.25, all over the square root of p 0.25, 1 minus p 0.75, all divided by 33. That's what calculators are for. Let's see what this guy looks like. Do a bracket. 0.18, subtract 0.25, close the brackets, divided by a square root, 0.25 times 0.75, divided by 33, close the brackets, and we get a z-score of negative 0.93. Now, when the alternate hypothesis is a less than, the z-score will always be negative. So if those two things match up, it means you've probably done it right. If this is a greater than story, right, p greater than something, the z-score will be positive. And there's reasons for that. This is called a left tail, right, test. So it's the guy to the left, isn't that where all the negative z-scores live? They're on the left. If it was a greater than, it'd be called a right tail test, and z's are positive when you go to the right. So there's our z-score. Now it's not too dissimilar from the ones we've done with z-scores before. We're now going to do the p-value, which is going to be what you were talking about, Bethany. Here's another example having to do that lower upper thing. Now the p-value is going to be the probability that I get a z-score less than a negative number. If this is less than, this will be negative and this will be less than. You notice the pattern. this is less than, z-score will be negative, and this will be less than a negative number. When this number is negative, on our calculator, we use this feature. It's called the normal CDF. You do a bracket, we do the lower, we do the upper, we do 0, we do 1. In this particular situation then, the lower number, I like to pick a number -9. But anything big and negative will do, right? -20 would be fine if you wanted to. The answer will be exactly the same, so it's not a big deal. Comma, the upper in this case is that guy, 0 and 1. So when it's a less than, you go -9, the number 0, 1. Right? So when it's a less than story, the -9, the number 0 and 1. Right. Now I got this guy already over here, so, oh, anybody want to tell us where you find this fella? Where do you find the normal CDF?
Second VARS or whatever that is.
Second, that thing, yes. Second distribution. So I think this is a bit cleaner than my little calculator. Can you see above the VARS button, there's a distri, it's short for distribution. It's in blue. So, oops, make sure the calculator's on. Second distribution. Choice number 2. And the number was -9. So make sure you hit that button when you want negative, not the subtraction button. So -9, comma, the number that we got for the z-score, -0.93. And then finish with 0 and 1. And that number, when I hit enter, is our p-value. And it is 0.176. Are we cool? Right, let's kick back to the paper. We're almost finished now. Now, if you have, imagine a totally different question, but suppose we had a z-score that was 1.97, right? Different question. And we were trying to find, you know, p greater than 0.3, right? That kind of alternate hypothesis, right? Then we would be getting our p-value by finding the probability that you get a z greater than 1.97, right? They match, and positive. And that would be normal, CDF. But when it's a greater than, it's the number first, then your 9, 0, and 1. Do you see the difference? Greater than a positive, less than a negative. When it's a negative, -9 the number. When it's a positive, number and 9. Right, that's the two patterns. Okay, ready for conclusion time. Is the p-value less than alpha? Is 0.176 less than 0.01? I think that's a big emphatic no, isn't it? Not significant, failed to reject H naught, not significant information, the usual kind of dots. Now, isn't it going to be really nice that SALT can do a lot of this for us? Well, that's what I'm hoping. So I'm going to go in now. Yeah. Pick. Gotcha. Okay, let's go. Right, let's get into our. I don't like that one. Don't like that one. I like this one. I mean, they're all pretty much the same, right? There's no big difference. I skipped the ones. The first two are really boring because basically they say, did you know that when you look at numbers from accounting and from everything, there's an awful lot of them that start with a 1 more than any other digit. And so sometimes what they can do is if somebody cooks the books, right, they can just have a computer scan through the numbers and see if there's any anomalies, like why isn't there as many ones as there should be? Because very often when you cook the books, you don't get the same pattern than you do if you have a normal business situation. Okay, I'm going to make this bigger so I can read it as well. It's tiny, a lot of reading. It's probably overkill. So first one we're doing is question 6. In this story, the national crime rate, is it really going down? Well, before COVID, the answer was yes. Evidently, not so much now. So is the national crime rate really going down? Some sociologists say yes. They say that the reason for this decline in crime rates from the 1980s through to the 1990s was demographics. That just means how many of each age group are in your population. America's quite a mature country. We are not by any means the oldest. There are some really, Japan's a good example. Do you know Japan is heavily democratically weighted on old? There are not that many young Japanese people anymore compared to the majority of older people. Scotland's very like that. I think France is another one. Brazil, on the other hand, is demographically very young. An awful lot of, teens, 20s and 30s, and not so many 70s and 80s. And that has a big effect because according to this, most people commit crimes in the age 15 to 34. So can you imagine if you had an awful lot of young people, you're probably going to have a high crime rate. Or if you have an awful lot of old people, you have quite a low crime rate. So that's what sociologists are saying, that the reason there's less crime is just that we're getting older as a country. Okay? According to the FBI, 70% of all arrests are males aged 15 to 34. That is a double statistic. Do you know that tells me something else? Don't guys commit crimes twice as often as women? So guys, for some reason, are more criminal-minded than girls. Denise, I'm putting you in a spot. How come guys commit twice as many crimes as women? Give me a good reason.
No idea, because women stay at home with their kids, or they're more not just staying at home, but they're
Nicer people. You could compliment yourself. You could say that women are more intelligent and women are less violent and women have got more common sense. Do you know that some of the stupidest things in the world are done by teenagers who think they're invisible or invincible? Right? They do some really dumb things. Now, not to say that there aren't girls who do dumb things, but they tend to do fewer dumb things and don't end up in jail because of that, allegedly. Right? So you're a sociologist in Rock Springs, Wyoming, okay? You get a random sample of police files, 34 arrests, 27 were males. So I'm writing that down, because isn't that basically p hat? 27 out of 34. You got that? 27 out of 34. And we're going to use a significance level of 5%. And the test is it different from the national average of 70%? Okay, I'm doing a quick decimal conversion here. 27 divided by 34 is 0.794 to 3 decimal places. Wow, okay, that sounds like it could be important, right? The average is 70% and looks like this place in Wyoming is 79%. So that's definitely different. It might be statistically significant. Now, the confidence or significance level is 5%. Now, which one of these is the guy that you're going to use when we want to test it's not the same as? Dot 1, 2, 3, 4, or 5. Which one of those is the guy to use? Not this. Agreed. Isn't it virtually the same kind of thought process that you do with means? Mu not equal to 45. You know that kind of thing? Have you noticed that the p's are always going to equal that number? So the null hypothesis would be that p is 0.70, and the alternate hypothesis would be p is not equal to 0.70. And that's what that funny little stroke is. Now, the next bit would have been sigma unknown student t distribution, right? Okay. In these guys, it's always standard normal, z-scores. And then they have this funny little fella. You cannot do statistical analysis on proportions unless you have enough people saying yes and enough people saying no. So NP is basically the number of people in your sample who said yes, and NQ is the number of people who said no. So if I go up to this data, 27 said yes, I got arrested. Doesn't that leave the other 7 to say no, I wasn't in that age group, right? So what we can do then is say it's going to be the standard normal, and it's always going to be that sense. So whatever, I mean, they'll jumble them up, it'll be position 1 the next question, but it's always going to be that sense. Standard normal, NP5, NQ5. Now, test statistic is going to be the z-score, and the p-value is going to be the p-value. So now I have to figure out, because I haven't done this yet, what it looks like when we hit salt. Well, it's going to go, oh, inferential statistics. One sample proportion. Okay. Now, the naming of it might be a little bit distracting, but number of successes just means how many people said yes, 27. Number of trials was what's the total number of people? In this case, it was 34. Can you see you have 27 out of 34 now? It's just written as 2 separate numbers. Our hypothesis test was based on a 0.7, and we were looking for not equal to. So won't that be not equal to 0.7? So you see how that's written. Very similar to what we did the last time. So when I hit this, shouldn't I get my z-score and my p-value? Fingers crossed. Go. And, oh, hey, that's a nice place to put them. I wish they'd done that with the other one, right? They're right in front of you. See them? 1.19, that's the z-score. 1.198, to 3 decimal places. And the p-value, 0.231 to 3 decimal places. So the z-score, which is the test statistic, was, oh darn it, it was 1 point.
How's it going?
I guess it's going well, but I'm sure you don't want me to say that. So I'll put you on mute in a second. 0.794, and the p-value was an unremarkable 0.231. Right. So in our picture, it's a very unremarkable, that one. And do you recognize these two guys as the same two guys that you seem to have every question you've ever seen in the last week? So we are looking for it being statistically significant, and we reject the null hypothesis. Or it's not statistically significant and we fail to reject it. Well, is 0.231 less than 0.05? No. So not statistically and fail to reject. So it's that one. And not significant, there we go. Are we good with that one? Right. Let's try another one with the class. These questions are pretty easy to do with the class, so that's kind of cool. I'm going to have to move these windows around as always. It's been a real pain. Right. Okay. Anybody got a good question to ask the class that you think isn't personal and they're likely to say yes, stroke no to?
How many people have like started listening to Christmas music or something?
Oh, okay. There are 35 people in this class now. Somebody just came. And I'm going to ask you then, stick your thumbs up if you've been listening to Christmas music, not just once, but, you know, deliberately looking to it. I got to admit, I'm looking for Christmas. 1, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 8. So p hat is 8 out of 35. So 8 divided by 35 is about 23%. Okay, what significance level? Which one of the ones, or do you want the 5 again?
Uh, 0.05.
Okay, we got a 5 in. I guess I need to make up a story. You're not meant to do it in this order, but I didn't know what the story was going to be. So I want to make the assumption, right, that is there enough evidence to prove that this is less than 30%? Right, so I'm giving myself a big gap. So 23 sounds like it might be able to make it, right? So we got an 8 out of 35, and we want to see, is that evidence to prove it is less than 30? So I should kick in here. I will just use this one. And one sample proportion. In this case, 8 people said, yep, out of 35 of you. It's a good number. I believe that it is less than 30. I want to prove that it is. Looks good. Right, if I generate the results, I get this Z statistic. And darn it in space, I still didn't get a significant p-value, did we? Can you see the p-value is 0.17? Isn't that not that small? You really want a p-value that's small. Okay, I'm going to cheat. Is there enough evidence to say that that's less than half of us? Right? I go for it. Yay, look at that p-value. Right, 0.00066. Would you agree that that is statistically significant? At least I've been able to prove that it's less than half of you who've been out there looking for Christmas music. Cool. You see that we now have a process where we can prove things. Let's go hunting for another one of their questions then. Oh, I'm not sure what screen I'm on. Let me double check. Okay. Oh, okay. Women athletes at a certain university have a long-term graduation rate of 67. So if you're in the women's basketball team, there's a 1 in 3 chance that you'll never even graduate. You'll probably get to play a lot of basketball, and maybe that's why, but you won't graduate. Well, you will. 2/3 of you will graduate, but 1/3 of you won't. Now, over the past several years, a random sample of 38 women at an athlete school, 21 eventually graduated. Does this indicate that the population proportion of athletes who graduates from the university is now less than 67? So it used to be 67%, and you're thinking it might have changed. So you go out there and you get a sample and you see what's going on. So I'm going to have to write down all the key numbers here. 21 out of 38, which I better turn into a decimal, is not good. That's 55%. Now, if 67 was bad, isn't 55 even worse? And we want to see then, does this indicate that the population who graduate is now less than 67, right? And the sigma is going to be 1%. So, significance level, 1%. That's a pretty high hurdle to get over. The null hypothesis, is it less than 67, is number 4, agreed? Less than 67. Are the 2 guys bigger than 5? Yes, they are. These 2 guys we're now going to get from Saul. Okay, where have you gone? One sample. The number of successes is 35. No, it isn't. It's 21 out of 38. We are testing, is it less than 67? Let's generate results. Okay, as a negative z-score, it's that guy. And the p-value is 0.06, roughly. So I will go here and I will tell you that the statistics, the z-score is negative 1.538, and the p-value is 0.06. Now, as a picture, we're looking for a less than, right? Correct, I should say. So it's that one. Okay. Is this p-value less than 0.01? No. And I know means the fail to reject, not significant, and insufficient. That's a bit of surprise to me. I would have thought that with a 55% pass rate, that was such a strongly different number, so much lower than 67, that it would have ended up being significant statistically. But actually, it wasn't. Well, not at the 1% level, at least.